So we will first see how we can test the model accuracy for regression, and then we'll see for classification. Now in regression setting, we see the average squared distance between the estimated value and the actual value. The smaller this value, the better our model will be. So MSE is given by the simple formula as shown here on the screen. Here we are differencing each predicted value from the actual training value and squaring it and then averaging it. MSE stands for mean squared error, and this is called as cost function in regression setting. We will use cost function everywhere in the modeling process. The purpose of cost function is to measure the performance of a machine learning model for a given data. So cost function quantifies the error between predicted values and the expected values and presents it in a form of a single real number so that it makes more sense to us and we can get a better idea of error. Now, depending upon the problem, we can either minimize the cost function or maximize it. The return value in case of minimization is called as cost, loss, or error. And in case of maximization, the return value is called as reward. Our objective here is to select the model with minimum MSE. So obviously, if the predicted response is close to actual response, then the MSE will be small. Now that we know that we have to minimize the cost function, the next question is, how do we do it? So for this purpose, we use gradient descent algorithm. We will see this algorithm later on in advanced modeling, but just keep in mind that we use gradient descent algorithm to minimize the cost function. Now let's say these blocks are our data. So when we build our model, we split our data into two parts. So let's say we split it into 70-30 ratio, or it could be any other ratio. But let's assume we have split the data into 70-30 ratio. So one part of our data will be used to build the model. That will be called as training data. And rest of the data we will use to test our model. So this test data is a new data for our model. And if it can give good results, then it means our model is working fine. Now this graph shows the behavior of test and training MSE against the flexibility. So as flexibility increases, there is a continuous decrease in training MSE. But the test MSE follows a U-shape. You can see this in the graph. This is the fundamental property that holds true irrespective of the data or method that we use. Now don't ask why or try to go into the details. We just have to know this property and keep it at the back of your mind. Also, we are interested in test MSE and not training MSE because training data is used for building the model. So the performance of model will always be better on training data. So as a rule, training MSE will always be less than test MSE. However, if training MSE is very less than test MSE, then something is fishy and it means we are overfitting and hence we need to relook into our model. So this was the case of model accuracy in case of regression setting. Now let's have a look at the classification setting as well. So here we will be predicting a class of a response. So which class our response variable belongs to, like we did in our previous example of identifying a cherry or not a cherry. So here we will not use MSE. Rather, we must quantify the proportion of mistakes that we have made using the estimate function f dash or f hat. Simply put, it is the classification of observations to a wrong category or misclassification error rate. It is given by an indicator variable as shown here, which is denoted by I. This simply means it will be equal to 1 if the classification is wrong. That is, if yi value of an ith response variable is not equal to yi hat. And it will be 0 if it is correct. That means yi value is equal to yi hat. So yi hat is the predicted class level for the ith observation using our estimated function f dash. For example, when we tested our model using the test data, if the actual ith observation, which is yi, is cherry, but our model predicted yi hat as not a cherry, then it will be counted as one misclassification. And if our model predicts yi hat is equal to cherry, when the ith observation of the test data yi is actually cherry, then it will be counted as 0. So similarly, we will calculate for the entire test data and find misclassification rate, which is basically total number of wrong observations divided by total observations. Now here also we will use a cost function, and this cost function is called as cross entropy or log loss. The formula is shown here on the screen. Now as a general rule, whenever you see a complicated formula, just remember that you don't have to remember it. This will make life pretty easy. So just have a look at the formula. We will have software to calculate it, but you should know what is happening in the background. Now here also we will use gradient descent algorithm to minimize our cost function. So gradient descent algorithm is a generic algorithm. We can use it to minimize any cost function. So that was all about model accuracy in classification setting.